Something was wrong with the universe. Not a flaw in the instruments. The telescope was perfect, a billion-dollar miracle of engineering, parked 1,000,000 miles from Earth, its golden mirror drinking in light that had traveled for billions of years to reach us. No. The flaw, if we can call it that, was in our understanding. In the summer of 2022, within weeks of opening its golden eye, the James Webb Space Telescope found objects that shouldn't exist. They were compact. They were impossibly red. And according to everything we thought we knew about how the universe works, they were far too massive to have formed in the time available. Scientists gave them a humble name: Little Red Dots. The name was simple. The implications were not. For 3 years, these tiny crimson specks have haunted astronomers around the world. Were they ancient galaxies, mature as our own Milky Way, somehow fully formed when the universe was still an infant? Were they something stranger, massive black holes lurking at the heart of creation, defying our theories of how such monsters could grow so large so fast? Or were they something we had never imagined? Something that would force us to rewrite the story of how everything, every galaxy, every star, perhaps even the possibility of life itself, came to be. This is the story of how a telescope showed us the impossible, how scientists followed the clues into uncharted territory, and how a tiny red dot named the Cliff may have revealed an entirely new class of cosmic object. The universe, it turns out, has been keeping secrets. It's time we learned what they are. To understand what the James Webb Space Telescope found, we first need to understand what it sees. Light travels fast, 186,000 miles per second, the cosmic speed limit. Nothing in the universe moves faster. But the universe is so vast, so incomprehensibly enormous, that even at that speed, light from distant objects takes time to reach us. The light from our sun takes 8 minutes to touch your skin. Light from the nearest star beyond our solar system, Proxima Centauri, takes 4 years. Light from the center of our own galaxy, the Milky Way, began its journey 26,000 years ago, when our ancestors painted horses on cave walls. And light from the most distant objects the Webb telescope can see? That light has been traveling for more than 13 billion years. It left its source when the universe itself was barely formed, a cosmic infant, less than 1 billion years old. When we look at these distant objects, we are not seeing them as they are. We are seeing them as they were. The telescope is a time machine, and the further it looks, the further back in time it sees. This is the extraordinary power of the James Webb Space Telescope. Specialized instruments detect infrared light, wavelengths stretched by the expansion of space itself during their billions of years' journey. Light that began as ultraviolet, as visible blue and white, arrives at our telescope as deep red, as infrared glow invisible to human eyes. Webb sees what Hubble could not. It peers through cosmic dust. It detects heat from the earliest stars. It reveals the universe in its youth. And almost immediately after it began its work, it revealed something that made astronomers around the world stop and stare. July 2022. The first deep field images arrived on Earth. Scientists expected to see distant galaxies, faint, diffuse smudges of ancient light. They expected these early galaxies to be small, still forming, mere seeds of the massive spirals and ellipticals we see today. What they found was different. Scattered throughout the images were tiny points of crimson light, compact, concentrated, surprisingly bright. At first, researchers like Joel Leha at Penn State thought they might be mature galaxies, old stellar populations whose stars had aged to reddish hues. But the math didn't work. If these were galaxies, they would have to contain stars packed together at impossible densities. As Bingji Wang, now at Princeton, calculated, the night sky from within such a galaxy would be dazzlingly bright, stars pressed so close together that collisions would occur monthly. That couldn't be right. By 2024, astronomers had catalogued 341 of these strange objects. They appeared in every deep field web examined, always in the early universe, between 600 million and 1.6 billion years after the Big Bang. And then, mysteriously, they vanished from the cosmic record. By 2 billion years after creation, they were gone. The little red dots existed only in a specific window of cosmic time. They appeared, they burned bright, and they disappeared. The question became, what were they? For decades, we thought we understood how the universe assembled itself. After the Big Bang, matter was spread almost perfectly evenly across space, a cosmic fog of hydrogen and helium. But almost is the key word. Tiny variations in density, quantum fluctuations from the first moments of existence, created slightly denser regions. Gravity did the rest. Over millions of years, matter flowed toward these dense spots. Dark matter accumulated first, forming invisible scaffolding. Regular matter followed, gas clouds collapsing, heating, eventually igniting as the first stars. These first stars were massive, violent, short-lived. When they died, they exploded, seeding the universe with heavier elements. From their ashes, new generations of stars formed, surrounded by planets, surrounded eventually by the conditions for life. This process takes time. Galaxies grow slowly. Black holes at their centers grow even more slowly, fed by infalling matter, limited by the pressure of their own radiation, pushing back against incoming gas. A supermassive black hole, the kind that sits at the center of most galaxies today, should need billions of years to reach its final mass. The universe simply doesn't allow shortcuts. Or so we believe. The little red dots broke these rules. When astronomers analyzed the light from these objects, splitting it into its component wavelengths, reading the chemical fingerprints encoded within, they found signatures that implied masses far too large. If these were galaxies, they were as massive as our own Milky Way, fully formed when the universe was less than 1 billion years old. To put this in perspective, imagine finding a fully grown oak tree in a forest that's only been growing for a week. The tree shouldn't exist. It can't have grown that fast. And yet, there it is. Massive, ancient-looking, impossible. Some researchers proposed that the little red dots contained supermassive black holes, active galactic nuclei, where matter spirals into cosmic drains at the centers of galaxies, releasing tremendous energy. This would explain the brightness, the compactness, the ancient appearance. But this interpretation ran into its own problems. Active black holes produce more than visible light. They emit X-rays, high-energy radiation from superheated gas just before it crosses the event horizon. They blast out radio waves. They vary in brightness as matter falls in chaotically. The little red dots did none of these things. They were eerily quiet in X-rays, silent in radio, steady in brightness. Whatever was producing their light, it wasn't behaving like any black hole we knew. The mystery deepened. By 2024, the scientific community had fractured into camps. each championing a different explanation. One group argued for ultra-dense galaxies, star factories operating at unprecedented efficiency, cramming more stellar mass into smaller volumes than we'd ever seen. Perhaps the early universe had exotic conditions that allowed such compression. A second group favored dust-obscured black holes. Perhaps there were supermassive black holes hidden in the hearts of these objects, but shrouded by so much intervening dust that we simply couldn't detect their X-ray and radio emissions. A third, more radical proposal emerged from theoretical physicists in China and the UK. Perhaps the little red dots weren't galaxies or known types of black holes at all. Perhaps they were something new, a phase of cosmic evolution we had never witnessed before. What everyone agreed on was this: to solve the puzzle, they needed better data. They needed spectra, detailed measurements of exactly how much light these objects emitted at every wavelength. They needed to peer inside the mystery. And in 2024, they got their chance. Anna de Graaf didn't set out to discover a new class of cosmic object. She set out to find answers. Working at the Max Planck Institute for Astronomy in Heidelberg, de Graaf helped design an ambitious observing program called RUBIES, the Red Unknowns, Bright Infrared Extragalactic Survey. The name was playful. The science was serious. Between January and December 2024, the RUBIES team spent nearly 60 hours of precious telescope time collecting spectra from 4,500 distant galaxies. It was one of the largest spectroscopic datasets ever obtained with the James Webb Space Telescope. Hidden within that data were 35 little red dots. Most had been spotted before in earlier images, but as Raphael Wieding, one of de Graaf's colleagues, would later say, the ones that were new turned out to be the most extreme and fascinating. And the most extreme of all arrived in July 2024. The astronomers called it the cliff. Located roughly 12 billion light-years from Earth, its light had been traveling since the universe was only 1.8 billion years old. But that wasn't what made it remarkable. What made it remarkable was a feature in its spectrum, a sudden, dramatic drop in brightness at a specific wavelength. Astronomers call this feature a Balmer break. It's a fingerprint of hydrogen atoms, absorbing light at particular energies where electrons jump between atomic orbits. Balmer breaks are common. We see them in old galaxies, where aging stars produce characteristic spectral signatures. We see them in hot young stars, glowing at specific temperatures. But the cliff's Balmer break was different. It was twice as strong as any previously observed. A precipice in the data, hence the name. De Graaf and her team tested every explanation they could imagine. Could this be an extremely dense galaxy, packed with aging stars? They ran the numbers. To explain the spectrum, stars would need to be crammed together so tightly that they would collide every few months. The galaxy would tear itself apart. Could it be a dusty, active galactic nucleus? They modeled that too. No amount of dust could reproduce the shape of that spectrum. The cliff didn't fit. It looked like nothing they had ever seen. And yet, it looked like something familiar. Here is where the story takes its strangest turn. When de Graaf examined the cliff spectrum closely, she noticed something peculiar. The overall shape, the characteristic V pattern, the extreme Balmer break, didn't resemble a galaxy at all. It resembled a single star. One impossibly large, impossibly bright star, glowing from the heart of the early universe. But how could that be? No star could be that luminous. No stellar atmosphere could produce that signature. Unless it wasn't a star in the ordinary sense. The model that finally fit the data was something astronomers had theorized about but never seen. They called it a black hole star. Picture a supermassive black hole, not the sleeping giant at the center of most modern galaxies, but a young, ravenous hole, still in its growing phase. Now surround that black hole not with a thin accretion disk of spiraling gas, but with a thick, dense cocoon, a spherical envelope of superheated hydrogen, so compressed it glows like the atmosphere of a star. The black hole is eating voraciously, pulling matter inward at tremendous rates. As that matter falls, it doesn't spiral in elegantly. It crashes through the envelope, releasing gravitational energy as heat. The entire cocoon lights up, not from nuclear fusion like a normal star, but from gravitational energy converted to light. From the outside, it looks like an enormous, impossibly bright star. But inside, at the center, sits a monster, a black hole growing faster than physics should allow. For years, one of the biggest puzzles about little red dots was their apparent mass. Based on the width of spectral lines, the spread of wavelengths in their hydrogen emission, astronomers calculated black hole masses in the billions of solar masses, masses that seemed impossible so early in cosmic history. In January 2026, a team led by Vadim Rusakov at the University of Copenhagen published a paper in Nature that changed everything. Rusakov's team looked more carefully at how those spectral lines were shaped. In most active black holes, line width comes from Doppler shift, gas moving at different speeds as it orbits the central mass. Faster motion means wider lines. Wider lines imply more mass. But the little red dots lines had a peculiar shape. They weren't bell curves, the signature of orbital motion. They were exponentials, straight lines on a logarithmic scale, symmetric and clean. This shape has a specific cause: electron scattering. When light passes through a dense fog of ionized gas, plasma where electrons have been stripped from atoms, photons bounce off those electrons. Each collision shifts the photon's wavelength slightly. The more collisions, the broader the final line. The little red dots weren't showing us orbital speeds at all. They were showing us something entirely different. Light scattered through impossibly dense clouds of electrons surrounding the central source. The implications were profound. When Rusakov's team corrected for electron scattering, the mass estimates collapsed. The black holes inside little red dots weren't billions of solar masses. They were between 100,000 and 10 million solar masses, 100 times smaller than previous estimates. These were still supermassive by any reasonable standard. 1 million solar masses is an inconceivable amount of matter compressed into a region smaller than our solar system. But these masses were within reach of theoretical models. They could form. They could grow. They didn't break the universe. The dense cocoons of gas explained other mysteries too. Why no X-rays? The cocoon absorbed them. Why no radio emission? Blocked by the surrounding material. Why so red? Light filtering through dense gas stretched to longer wavelengths. As Rusakov explained, this cocoon makes these black holes look red and prevents much of their radiation from escaping. Without the ionized gas, the data simply don't make sense. The pieces were falling into place. But the most exciting implication wasn't about masses or spectra. It was about time. Little red dots exist only in a specific window of cosmic history, appearing around 600 million years after the Big Bang, disappearing by 2 billion years. They are brief, transient, a phase. What Rusikov's team had revealed was this. We weren't looking at mature black holes, the kind we see at the centers of galaxies today. We were looking at black holes in their infancy. Cosmic children, still wrapped in their birth cocoons, still growing toward their final masses. For the first time in history, we might be seeing supermassive black holes being born. Not fully formed, appearing mysteriously in the early universe, but actually growing, right before our eyes, shrouded in the dense gas that feeds them, glowing from the violence of their formation. And if that's true, then the little red dots aren't universe breakers after all. They're universe builders. For decades, astronomers have debated a cosmic chicken and egg problem. Which came first, galaxies or their central black holes? The traditional view held that galaxies formed first. Gas collapsed, stars ignited, and over billions of years, some of that material spiraled inward, slowly building the black holes we see today. Black holes were products of galaxy evolution, consequences, not causes. But the little red dots suggest something different. If these objects are young black holes wrapped in cocoons of dense gas, black hole stars still in their formative phase, then black holes might have formed first. They might have been seeds around which galaxies later grew. Picture it. In the dense conditions of the early universe, matter collapses directly into massive black holes. These holes begin feeding immediately, surrounded by thick envelopes of gas that make them glow like enormous stars. As they eat, they grow. As they grow, they attract more matter. And around them, over billions of years, galaxies assemble. Black holes as cosmic architects. Monsters that build cathedrals. This isn't proven yet. The debate continues, and science demands evidence before conclusion. But for the first time, we have objects that might preserve clues from the moment of formation. Chemical signatures, physical properties, traces of their origin. As Rusikov said, if we are lucky, little red dots may still preserve clues from the time when they were formed. This is one of the biggest remaining questions in astrophysics, and it seems that we are closer than ever to being able to answer it. There's another mystery hidden in the story of the little red dots. Their disappearance. They appear in the early universe, abundant and bright. Then, around 2 billion years after the Big Bang, they vanish from the cosmic record. What happens to them? The black hole star model offers an explanation. A black hole can only remain wrapped in its dense cocoon for so long. Eventually, the hole eats through its food supply. The envelope thins. Radiation begins to escape. The characteristic redness fades. What was once a little red dot becomes something else. Perhaps a regular quasar, blazing with X-rays and radio waves as its accretion disk is finally exposed. Perhaps a dormant black hole, its feeding frenzy complete, settling into quiet residence at a galaxy's center. The little red dots might be just one stage in a cosmic life cycle, a brief, fiery childhood before maturity sets in. Every supermassive black hole in the universe today, including the 4 million solar mass giant at the center of our own Milky Way, might once have been a little red dot. A cocoon-wrapped infant, glowing in the darkness of the young universe. We might be seeing the baby pictures of cosmic monsters. But we must be careful. Science is a process of discovery, not a collection of final truths. The black hole star hypothesis is compelling. It explains more of the data than any previous model, but it is not proven beyond doubt. Some astronomers have proposed alternatives. In July 2025, a separate team suggested that little red dots might be supermassive primordial stars, population 3 stars of perhaps 1 million solar masses, metal-free giants seen in the last millennia of their lives. These too would show strong Balmer breaks. These too could be progenitors of black holes. Others argue that electron scattering might not be the whole story. Different little red dots might be different things. Some cocooned black holes, some dense galaxies, some phenomena we haven't yet imagined. The universe is much weirder than we can imagine, as Joel Leha reminded us, and all we can do is follow its clues. There are still big surprises out there. What matters is that we're looking, that we're questioning, that we're willing to be wrong, to revise our models, to let the universe teach us what it actually is, rather than what we assumed it would be. Let us, for a moment, step back from the puzzle. We have been discussing objects billions of light years away, processes that occurred billions of years before our planet formed. Numbers so large they lose meaning. Distances so vast they become abstractions. But there is a connection between those ancient crimson dots and the world we know. Every atom in your body was forged in a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it cooked in stellar furnaces and scattered across space when those stars died. You are, quite literally, made of star stuff. And the stars that made you? They formed in galaxies. And those galaxies? They may have assembled around seeds, around black holes that once glowed red in the darkness of the young universe, wrapped in cocoons of superheated gas, growing toward the masses they would one day achieve. The little red dots are not just puzzles to solve. They are ancestors. They are chapters in the story of how matter organized itself across billions of years into worlds capable of wondering where they came from. There is something almost miraculous in what we've done. A species of clever primates evolved on a small rocky world orbiting an ordinary yellow star in the suburbs of an average spiral galaxy. We built a machine. We sent it 1 million miles from home, and through it, we looked backward in time, 13 billion years, to see objects that existed before our sun, our planet, our galaxy as we know it, had formed. We found something that didn't fit our theories. And rather than ignore it, we changed our theories. We proposed new ideas. We tested them against data. We argued, revised, and tested again. This is the great project of science. Not certainty, but inquiry. Not final answers, but better questions. An endless conversation between human minds and cosmic reality. Each observation teaching us something new about the universe we inhabit. Carl Sagan once wrote that we are a way for the cosmos to know itself. Through us, the universe achieves self-awareness. Matter contemplating matter. Starlight studying its own origins. And in that sense, the little red dots matter. Not just as scientific puzzles, but as pieces of our own story. We are the universe, looking back at its own childhood. The James Webb Space Telescope continues its work. Every month brings new observations, new data, new surprises. Anna DeGraff and her team have been granted more telescope time to study the cliff and other extreme little red dots. The questions are sharpening. The answers are coming into focus. We may learn, in the years ahead, exactly how supermassive black holes are born. We may witness the seeds of galaxies, caught in the act of formation. We may discover that reality is even stranger than the black hole star hypothesis suggests. Whatever we find, one thing is certain. The universe is not done teaching us. Look at that tiny crimson point, 12 billion light-years away, 12 billion years in the past, a cocoon of fire around a growing monster, burning in the darkness of cosmic dawn. It carries a message across unimaginable distances and incomprehensible ages. And the message is this: the universe is stranger than you imagined, more beautiful than you knew, and there is always, always more to discover. We are made of star stuff. We are a way for the cosmos to know itself. And the cosmos, it seems, has secrets still to share. This is Cosmic Canvas, where we trace the light back to its source. Until next time, remember that what breaks our theories often builds our understanding.